Okay, great. Hi, everyone. Thank you for taking the time to join this webinar on quantum optimization with arbitrary connectivity using neutral atoms. So in this webinar, we're going to tell you more about our new methods in encoding a wide range of optimization problems in neutral atom quantum computers. So with this new results from Quora and collaborators, we expand hugely the application space of neutral atom quantum computers in the optimization space. Great. This is your host today. My name is Shengtao Wang. I'm the Quantum Algorithm and Applications Manager at Quora. I've been leading the efforts on algorithm and application development at Quora since the start of the company. Joining us today, we also have Jonathan Worth, who is a member of the algorithm and application team. Jonathan's focus is on developing near-term algorithms and applications that can fit on today's hardware. A very brief agenda for today. So I'll first tell you more about Quora and our neutral atom machine, 256-qubit machine online, which is called Aquila. And then I will hand over to Jonathan, who will tell you more about Ripper blockade and how that's related to a particular optimization problem called maximum independent set problem. So we'll also tell you about our seminal result together with Harvard last year, showing quantum speed up compared to classical simulated annealing algorithm and results there. So the focus of today's seminar, though, is on this new encoding method that we can do optimization beyond unit disk graph and beyond MRS, and Jonathan will tell you more about that. Lastly, we'll have a few minutes of Q&A. A gentle reminder for everyone, if you have any questions, please feel free to post in the Q&A box below on the Zoom chat. We'll try to answer questions live, and also after the seminar, we'll have a few minutes for Q&A as well. Great. Let me tell you first more about Quora. For those who doesn't know anything about Quora, we build quantum computers based on the neutral atom technology. We're based in Boston with 40 plus scientists from top tier universities like Harvard and MIT. Our first neutral atom quantum computer with 256 qubits machine is now publicly accessible on Amazon Braket. It is also the only publicly accessible neutral atom quantum computers available to the public. We try to focus on delivering real life values at every stage of the development and aspire to do the best way to quantum. So if you have any use cases that you think that can benefit from neutral atom quantum computer or just quantum computer in general, please feel free to talk to us. We really try to bring out value at every development stage before really we have fully fault-tolerant quantum computing at the end goal. All right, very quick overview of the timeline of Quora and how the technology developed in the past couple of years. So the dream starts around 8 years ago by now. Harvard physicists start building neutral atom machine as a building block for quantum computers. And in a short 2 years, Harvard has demonstrated and control over 51 qubits in one-dimensional, and this is a seminal result with a large neutral atom quantum computer in one dimension and a lot of control. And Harvard, and in a few years, they demonstrated high fidelity integrating gates. This is a building block for quantum computation and largest GHZ state. And there are a few breakthrough results in fundamental physics in 2021 as well. So for Quora, we spun off out of Harvard and MIT in 2019. And we built our first neutral atom quantum computer in 2 years, and then it's publicly available last year in November. And everybody can log into Amazon Braket now and to run jobs on Aquila. And feel free to play around with Aquila and see what use cases you can help with your case. And last year, together with Harvard, I mentioned that we report the first quantum optimization scaling advantage favorable to simulated annealing, and Jonathan will tell you more about this later. I'll just very briefly mention that there's a new architecture with dynamical connectivity demonstrated last year as well. We won't mention too much about that today, but it's also a new architecture for fault tolerance quantum computer in the future as well. Great. Before we delve into the details of encoding and so on, let me just tell you about some fundamental building blocks of neutral atom quantum computers. So we have, first of all, atoms, which encode the qubits, and then we have optical tweezers that can trap the atoms. And then we really make use of the Ripper blockade phenomenon to entangle the qubits. What does that mean? First, imagine you have an atom and then a beam of laser. The beam of laser optical tweezer can trap the atoms. And in this atom, first you can image the atom and see it on the camera. In this atom, we use 2 atomic levels to encode the qubits. In this case, one in the ground state and one in the Ripper state. As a qubit, we can use a laser to coherently drive between these 2 levels and do gates between them, like schema X gates and so on. The Ripper state is a highly excited state with a large electron cloud, and they interact with each other. If we imagine we have 2 atoms far away from each other, and both of the atoms can be excited to the Ripper state, and they don't have much interaction between each other. But if we bring the 2 atoms close to each other, in this case, the large interaction between the Ripper state will actually block the other qubits from exciting to the Ripper state. So this is really what we make use of called Ripper blockade to entangle the qubits. And for both digital quantum computing and also for analog quantum computing, this is a major entanglement mechanism as well. Okay, all right. What is analog quantum computing? For Aquila right now, the major mode of operation is analog quantum computing. And what that means is we have controls of the laser beams which actually describe parameters in Hamiltonian. For our case, this is a Ripper Hamiltonian written in this form. We have a laser that control the Rabi frequency and the phase of the laser and then the tuning of the laser. These are all time dependent. You can control the time dependent traces of these parameters. And there's an interaction term which governs the Ripper blockade phenomenon. And you can think about analog computing as really a big gates that acting on all the qubits together, and that can entangle the qubits very efficiently and very fast. For doing gates, you can think about it as this kind of a bang protocol with on and off protocols, and now you can do gates on individual qubits. But a Newton protocol is more or less a smooth function of the parameters with parameter pulse shapes, but we can do much more. We can do like an arbitrary pulse shape, and you can design algorithms that tailor to particular use cases that combine gates and Newton behavior in this case. And kind of more interestingly, we have programmable connectivity, which that means like we can position atoms in a 2-dimensional structure and encode different problems by encoding positions of the atom in any different geometry. In this case, you can see we can encode different geometries and even a word map by placing atoms in particular positions and have this hello world kind of example using atoms to run Aquila. All right, I will now hand over to Jonathan, who will tell you more about optimization and Ripper blockade. And I'll also remind everyone, you can feel free to ask questions in the chat box, and we'll answer them live.
All right. Can everyone see can you see my screen? Good. All right. Thank you very much, Shengtao. I guess I will continue. So in the previous set of slides, we described how a bit of how Aquila works and our neutral atom hardware works. And now in our second half, we will talk about a particular application. So a good place to start is with my favorite problem, which is something called maximum independent set. And the general challenge, which is one of combinatorial optimization. So what combinatorial optimization is suppose we have some some objective function over some very large space of possibilities. For example, over all binary bit strings of, say, 50 bits, right? That is an exponentially large space of possibilities. And usually this means that we need to more or less search through all of these possibilities to find a good solution. My favorite example of this is something called maximum independent set, which is a graph-based problem. So if we have some graph over here, the goal is to find the largest subset of vertices such that no two vertices are adjacent. So for example, here we have some graph of vertices and edges. And we want to find the independent set, or this set of red vertices, such that no two vertices are adjacent, and such that I choose the largest number of these vertices. And it ends up that this is a prototypical NP-hard optimization problem. And you can imagine that trying to find the maximum independent set of these graphs ends up sort of scaling exponentially with the number of vertices, which is more or less trying to find all the possibilities of vertices in and out of the independent set. Now, this problem is really nice because we can map it to something, we can map it to our Rydberg blockade. So this comes from the insight that the Rydberg blockade is equivalently an independent set constraint in the low energy subspace. So what we can see is we have this local term plus this interaction term. And we can imagine if our two atoms are within some distance of each other, then they're mutually blockaded from both being in the Rydberg state. So in this way, if we have some logical graph over here, say this graph where this is the independent set, then we can imagine we take the low energy subspace of the equivalent set of atoms, right? And the low energies of this can be chosen to be the independent set subspace. So in this way, we can do our excitation of the atoms so that, say, these atoms here are all driven into the Rydberg state, and all of the rest are blockaded from going into the Rydberg state. And in this way, we could make it so that the ground state of our Hamiltonian encodes the solution to our optimization problem. Then, given this insight, and now we can encode this ground state to solve the problem, we can then do an algorithm to prepare this ground state. So the simplest algorithm to do this is something called adiabatic state preparation. So in adiabatic state preparation, what we do is we slowly change the parameters of our Hamiltonian. And if we change them slowly enough, then under something called the adiabatic theorem, the initial ground state of the Hamiltonian follows the instantaneous ground state of my time-dependent Hamiltonian, and finally evolves or anneals to the final ground state of my target Hamiltonian. So in this case, what I do is I turn on my Rabi drive, which is my the term which generates superposition in my system between the ground state and my Rydberg state, and I slowly turn that on. And then what I do is I ramp my detuning from negative, where it's energetically preferred for all of these atoms to be in the ground state, to positive, where it's energetically preferred for each of the atoms to be in the Rydberg state. And then I choose my detuning in such a way such that the final detuning encodes, and then I slowly turn off my omega, so that then the only term left is this diagonal term. And this diagonal term we can choose to encode, or choose such that it encodes the ground state of my optimization problem by encoding the position of each atom. Now this is the algorithm. Now the first exciting results on this came out of results from Harvard, which came out early mid last year. And there they chose a particular kind of graph, in particular this maximum independent set on King's graphs with random dropout, or defective King's graph. It's called a King's graph because you can imagine it's neighbors and nearest neighbors, and this is how a king can move on a chessboard. And the challenge is, on this graph, can we find the largest number of vertices that generate an independent set? And it ends up that this is actually a pretty hard problem. So this solution here, which is, I believe, the maximum independent set of this graph, was actually generated on Aquila. So we used our own device to generate this solution. So we can take this problem and we can try and compute the performance and analyze the performance of these graphs, in this case for this paper on Harvard's machine. And as well as that, we can also try to optimize the protocols which try and do this state preparation. So in particular, our collaborators at Harvard did two protocols. One is QAOA, or the Quantum Approximate Optimization Algorithm, which is a variational algorithm, and also a variational adiabatic protocol, which varies the annealing schedule as a function of time. And we can see that as a function of time, or the effective depth p, we see some improvement in the performance. And then at very large depths, we see a detriment in the performance due to decoherence effects. But you can see that actually this sort of effective depth, which is more or less the number of pi times that you flip between the ground and the Rydberg state, ends up being relatively large. And for an n-log system, you can draw an analog for this effective depth to sort of the effective gate depth in the system. So we actually have very relatively large gate depths while still maintaining coherence in our system. Now, what we can see is once we variationally optimize these protocols on this particular kind of graph, we can analyze the performance and we can compare it to equivalent classical algorithms. So in this case, we choose an algorithm called simulated annealing, which is a similar algorithm which randomly chooses vertices on the graph. And then we see that the time to solution of the performance of this algorithm ends up scaling as some sort of hardness parameter, which is plotted here. And we find that for the simulated annealing algorithm, we find that the scaling goes as the inverse of the hardness parameter, or CH to the -1. However, we see that for a particular type of problem instance, we see a speed up in the performance. In this case, instead of going as to the -1, we see it as going as, say, to the -0.63, which is sort of reminiscent of a Grover type square root speed up in the performance of the algorithm. And this is the first hint at a quantum speed up in solving optimization problems on large problem instances. So this is some very exciting results. This is sort of the main plot here. You can see that for particular choices of graphs, we can see that for one class, we see this linear scaling. But then for another class, we see this quadratic speed up. This is the results out of Harvard. Now we can also do these same problems on Aquila, but we actually have extra flexibility on Aquila. In particular, instead of being on these square grids, which is this King's graph, we can actually arbitrarily position each atom. And what this means is this lets us have extra flexibility in our problems. So for example, let's suppose we want to choose possible locations of stores in Manhattan, right? And say this is some simple problem. And we want to make it so that no two stores are within 1,000 meters of each other, say. This ends up being this independent set constraint, and now we want to have the maximum number of stores within that particular constraint. Then what we can do is we can use our arbitrary positioning of atoms, right? So now here is our problem encoded in atoms, right? This is a picture of individual atoms on Aquila. And we can do our evolution, excite the atoms to the Rydberg state, do our measurement, and this lets us find the answer, so that this is our maximum independent set of 14 vertices on this particular graph. And this gives us an extra flexibility over the previous generation where we have this arbitrary position. Great. So now let's ask, can we go beyond unit disk graphs? So for in this previous work, we had this hardware native mapping, which is the maximum independent set on unit disk graphs. But of course, this is not everything. There are many, many interesting problems which are not unit disk graphs and are not independent set problems. So this brings us to the key idea of this work, which is that in the same way that we can encode the solution in this hardware native mapping, we can also encode the solution to general optimization problems in the ground state or the maximum weighted independent set of some unit disk graph. So for example, let's suppose we have some graph of vertices and edges, which is not necessarily a unit disk graph. Then what we can do is we can encode this problem as a maximum weight independent set. Then once we encode it, then we can use Aquila to prepare the ground state. We can then take measurements of that, and then we can map that bit string back to the problem solution. So in this way, we can use our quantum computer to solve these general optimization problems. Now, of course, natural question is, how do we do this? And our method is something called a gadget. So the fundamental idea is to represent each bit as a 1D string of atoms. So for example, if we have this 1D string, then we can label all of the odd vertices, say, as a logical 1, or all of the even vertices as a logical 0. Then what we can do is we can use these objects, which are now like non-local and can be spread over a 2D system, and we can weave these together into something like that we like to call crossing ladders. So for example, if we had bit 1, right, then you can see that in this crossing lattice, bit 1 crosses over every other bit in the system. So for example, if we have an interaction in some graph between 1 and 4, then we can simply label this interaction where they cross. So one key insight that we have is this idea of gadgets. So if we have, say, a crossing between this non-unit disk thing here, we can design some unit disk gadget which has the same behavior, right? So for example, if 1 and 3 do not interact, we can simply replace that crossing with this particular gadget. Now we can introduce interactions by modifying these gadgets. So for example, for a QUBO, or quadratic unconstrained binary optimization problem, what we can do is we can add the quadratic weight between, say, vertex 1 and 2 by biasing the weights of the maximum weight independent set. Or equivalently, if we want to do a maximum independent set, so we have an independent set condition on some set of vertices, and we can choose some other gadget to encode this, say, this particular independent set constraint. And in this way, this lets us map a general optimization problem, or a general graph optimization problem, onto this weighted independent set. And how we do this is we have this general problem, right? So of vertices and edges, and we map this onto this crossing lattice, and we map this onto positions and weights of each individual atom. So then you can see that sort of the positions of each atom here correspond, each vertex here would then correspond to the position of each atom in the array. So this is the general idea. Of course, this comes with a few challenges. The first, and this is a great objection, you raise your hand and say, Jonathan, wait a second, isn't this a horrible overhead? And in fact, it is. Here, if you have an arbitrary connectivity graph, then generally your scaling overhead in the number of vertices in your encoded graph grows quadratically with the system size. So for example, if you had, say, 10 atoms, or 10 vertices, you need of order 100 vertices, and 100 atoms to encode it. This means that in the limited real estate that we have on Aquila, which is 75 microns of our objective and then 4 microns of spacing, this means we can only fit a relatively small number of encoded bits. However, one can imagine that this has a lot of extra things associated with it. For example, here we kind of accidentally string out this 1 bit here way too far, and we can sort of pull that back in, or we can pull these guys back in, or we notice that this crossing gadget isn't doing anything, and we can iterate and simplify this graph into an equivalent much smaller graph, which still solves the same optimization problem. So in this way, we even though the naive mapping may only do a few qubits or a few bits, more efficient mappings may do more. Second challenge and question is one of hardware efficient instances. So of course, the most hardware efficient would be maximum independent set on unit disk graphs. But not everything is a maximum independent set on a unit disk graph. But what we can do is we can choose problems which have the same geometric connectivity as our 2D space. So for example, if we have this this restricted connectivity Kubo problem, right, where we only connect vertices between neighbors, then we can take this problem and map this onto the same size of hardware that we mapped those 5 bits onto. So in this case, this is 50 bits, which we can then map onto the same 75 by 75 micron space to solve larger problems. And finally, and I think this is a really interesting thing, is thinking about encodings beyond graphs. So in particular, there's this idea of integer factorization. So if we, which is as follows. Suppose we have some 2 prime numbers, p and q, and we multiply them together into some number m, right? This number m can be uniquely factorized back into p and q. And actually doing this factorization is so hard that it is the basis of modern encryption. So plenty of people might be interested in solving it. So what we can do is we can take this multiplication of p and q into m, and we can break this into a binary multiplication, which is equivalently some system of equations, which we can write down here. And then the trick is we can take this system of equations, and by just sort of looking at it carefully or iteratively finding gadgets, we can find some gadget which encodes this system of equations in its constraints. So the maximum weight independent sets of this gadget encode all of the valid solutions to this equation. Then what we can do is we can take this gadget and we can tile it in such a way that, for example, if we want to figure out the unique factorization to the number 6, right, we can take this set of atoms and we can look at the solution, the maximum weight independent set of this set of atoms, and we can say, oh, 6 equals 2 times 3. And in this way, we can encode general constraint satisfaction problems as well as just graph problems. So in summary, I would like to conclude here. So in our previous work with our collaborators at Harvard, we were able to solve maximum independent set on unit disk graphs. And now in this work, we show that we are able to reduce general optimization problems to this maximum weight independent set. And this comes with 3 key insights. The first is this idea of a crossing lattice, which lets us interact every bit with every other bit, though there are ways to compress this down and make it more efficient. The second is this idea of gadgets, so we can encode general constraints into these gadgets. And then finally is using these 2 tools and to compute the solution via our neutral atom hardware, such as Aquila. And what this does is this enables solving general optimization problems with whereas Aquila hardware as well as neutral atom quantum computers. And with this, I would like to conclude and take any questions that anyone may have. So I invite people to ask questions. At this time, I would like to invite people to ask questions in the Q&A chat. And I think, Shengtao, you can tell me if there are any...
Yeah, thank you for asking questions in the Q&A chat. We have quite a number of questions, actually. We have 1 or 2 minutes to answer some questions live. Let me see. How about this one? Emma asked, how do we assign weights to the vertices in Aquila? Would you like to take that question, Jonathan?
This is a great question. So when we describe the Hamiltonian, right? So like in the end, everything is atoms and lasers, right? So we have one set of lasers which does this Rydberg, which lets us jump between the ground and the Rydberg state. But then what we can also do is we can set another laser, which is actually like multiplexed and targets every individual atom. And we can choose this laser such that it individually detunes each atom by basically choosing the amplitude of the laser light at that point. And in this way, we can define an individual local detuning on every atom in the array. So that's a great question. And this is something which will hopefully be an upcoming feature on Aquila.
Yes, just to emphasize this again, so we have a new capability coming out, which is called local detuning feature, which will enable us basically to assign weights to the vertices in Aquila. Maybe one quick question. again, people ask about, they saw a Julia-based SDK. Is there anything on Python? The answer is yes. We have a Bragcat SDK as well. That's a Python SDK. You can access the machine through Bragcat with a Python SDK. All right, there are still a lot of interesting questions and exciting questions. But we'll probably stop here and let people go. We'll continue to answer questions on Q&A, on Zoom for a few minutes. And then you're always welcome to reach out to us and contact us. If you have any use cases, if you have any interesting problem that you want to solve using neutral atom computers, please reach out to us. Thank you for joining us in the webinar today. Wish you a great day, everyone.